Looking now at exercise 5.1, transformations, it's rendering the same thing, except now it's being transformed. It's being rotated around its z-axis and then translated away from the origin. So the first thing that's different here is in our vertex shader, we are now going to have a uniform, which is a map 4. It's a 4x4 matrix representing a transform, and we're going to apply that transform onto our position vector by multiplication. And that is what we are setting to the GL position. In C++, we're going to bring in a new dependency, GLM, which is the OpenGL mathematics library. It's not officially part of OpenGL, but it's used in conjunction with OpenGL. And GLM is going to bring in for us some vector and matrix types so that we can work with vectors and matrices in a convenient form. With this new dependency, we're going to create a transform value of 4x4 matrix, and that is what's going to be set for the value of our uniform. And note here it's uniform matrix 4VF. That's what allows us to set a 4x4 matrix as the value of the uniform. Now to set up the transform, we're combining two prior transforms, translation and rotation. So translation we're creating first with a call to translate, and in the call we specify a vector of 3 floats, denoting translations for the x, y, and z axes. But the first arg is another 4x4 matrix, and what the call to translate returns is this matrix multiplied with the translation matrix that is set up as defined by this vector. And this is really quite strange to me because it has then the effect of creating a new translation matrix and then applying onto it another transform matrix. In this case, calling map4 with just a single float value of 1, that sets up an identity matrix because we don't want the translation matrix defined by this vector to be transformed. We just want it as is. So when the multiplication is done, it's the identity matrix times this new translation matrix, and that's what we get back. For the rotate function, it's a similar deal. You pass in a vector of 3 floats, which represents an axis of rotation. The second argument is the angle of rotation around that axis. I assume expressed in radians rather than degrees, but I'd have to check. And the first arg is another 4x4 matrix, just like with translate. And so what gets returned from rotate is not necessarily the rotation matrix defined by these two parameters, but that rotation matrix multiplied with transform. And again, in this case, we don't want it modified, we want it as is, so we're passing in an identity matrix for the first argument. So with our translation and rotation matrix, we want to combine them, and because we want the rotation performed first and then the translation, it's translation times rotation in that order. If you flip the order here, it would apply the translation and then the rotation, and you'd get a different end result. Now, because we just want to see the rectangle spin, the angle is just the time. And of course, because time advances at an even rate, then this number gets bigger and bigger at a steady rate, and so this will make the rectangle rotate at a steady rate. So this is how we can set up the transform matrix, but if I comment this out, uncomment here, if instead we create our translation matrix, and that is what we pass as the first argument to rotate, then what rotate will call will effectively be this first matrix multiplied by the rotation matrix, and that then will be what transform is assigned when we get down here. Same result as we had up here. Notice that effectively we're combining our transforms in reverse order. The one that we're defining here first at the top, translate, that is the one that's applied last. So it's in backwards order. And I still do find it strange that they do the multiplication this way. I would expect it to be the other way, but nope, this is how it works. Now, if we look at 6.1 coordinate systems, we are finally doing a 3D projection. A rectangle here has been rotated on the x-axis, and also the camera has been moved back a little bit. So now in a vertex shader, we're going to have 3 separate 4x4 matrix uniforms, one for the model transform, one for the view transform, and one for the projection transform. We multiply projection times view times model times the position, and again remember that means that effectively the model transform is applied first to the vector, then the view transform, and lastly the projection transform. Now it may occur to you that we can combine these matrices together all in one go before starting our shader. If they're not going to change from one vertex to the next, it's wasted work to compute the same thing over and over again for each vertex. Down the line, when things get more complicated and we start accounting for lighting, it's going to be the case that for each vertex we want to compute not just the clip space coordinate, but also its view space coordinate. And so we're going to keep the projection matrix separate from the view and model matrix so that we can separately multiply a combination of view and model to get the view space coordinate, and then apply the projection transform on that to get the GL position, the clip space coordinate. So in practice, it is common to combine view and model together and feed that into the shader, but we're generally going to keep the projection separate. In this case, for just simplicity and demonstration, we're keeping them separate. And so we're feeding in 3 separate Mat4 uniforms to the vertex shader. So to set up these uniforms on the C++ side, we're creating a model transform, a view transform, and a projection transform, and then we're setting each one to the respective uniforms. What's being demonstrated here is 3 different ways to do so. In the first case, when we call uniform matrix 4VF, we're using this value pointer function from the GLM library and using that to get a pointer to our model matrix. Alternatively, in the second example here, we're simply just getting a pointer to the first byte of the matrix. The matrix has a subscript operator defined such that you can access its columns and rows with the subscript operator. And then for the third case, the shader class that's been defined has a convenience method set mat4 for setting a mat4 uniform, in this case, with the name projection and the value of the projection matrix. So what about these matrices? Well, for the model matrix, what we're doing is we just want to rotate a little bit on the x-axis. So here, the rotate function, we're specifying a vec3 of the x-axis. The angle is -55 radians. And again, we're just plugging in an identity matrix because we don't want this rotation modified. We just want it verbatim. For the view matrix, we want the camera to move backwards. Otherwise, we're not going to see anything because if you recall, our rectangle is starting on the XY plane, so we need to move back to see it. So to move the camera backwards, you would add to the Z value. But of course, we're not actually moving the camera. There is no camera to move. We're instead moving everything in the world in the inverse way. So in the view transform, we're going to move everything down the negative Z-axis. We're going to add -3. Now, where things get complicated, at least if you want to fully understand it, is setting up a projection matrix. We're calling here perspective, which will return the perspective matrix, which is defined such the horizontal field of view, what the so-called FOVY, F-O-V-Y, is 45 degree radians. It has an aspect ratio for its view plane, which is equivalent to the aspect ratio of our output resolution, 800 by 600. The near clipping plane is defined at 0.1, and the far clipping plane is defined at 100. And with this information, the perspective function can return a projection matrix. And this may be confusing because it's different from how I explained projection. I explained projection in terms of a defined focal length and a width and height of the viewport. But here we're not plugging those values in. Instead, we're plugging in an angle for the field of view, the horizontal field of view, FOVY, FOV, and an aspect ratio for the view plane. What's happening is from those 2 pieces of information, the perspective function can compute a focal length and a width and height for the view plane. Looking at this illustration, you can see that the rectangular cone of vision is diagrammed as a 4-sided pyramid. And you see also where our near plane is defined and the far plane, creating our frustum. And the angle in this pyramid between the top side and the bottom side, that is the FOVY, the horizontal field of view. And though we haven't defined any focal length, consider that for this cone of vision defined by the field of view, the view plane can go anywhere in the pyramid. Any rectangle bounded by the pyramid that's parallel to the XY plane would be a valid view plane. And so in the diagram, they are designating effectively the near clipping plane to also be the view plane. But understand it would be the same projection if instead our view plane were defined to be the far clipping plane instead. For a given projection, there's not just one possible combination of view plane width and height and focal length. As the focal length increases, the width and height scale up, and as the focal length decreases, width and height would effectively scale down. We have effectively a whole continuum of options. What's usually done, however, is we just simply select the near clipping plane to be our view plane. And so then for our projection matrix, we can compute what the focal length is. It's simply equal to the length of the near clipping plane. And then with the little trig, we can compute half the height of the view plane and half its width. Because the z-axis through the view plane forms a right triangle with the top of the pyramid, we get the tangent of half the FOVY and multiply that by the focal length, which again is equal to n, the distance to the near clipping plane. And that gets us half our height. because we also know what the aspect ratio between the width and the height is, once we have half the height, we can then multiply it by that ratio, that aspect ratio, to get half the width. And so now we have all the information to set up our projection matrix, following the formulas I showed you to get from view space to clip space. Because we now actually want to compute our projection matrix, I'll show you exactly how to compute the z of the clipping plane. So the problem again is that we want to scale z values from the range of n to f into the new range of -n to f. And we can do that first by adjusting the z values to a range that runs from n to f, but oriented on 0. So we subtract n from z. And then for that adjusted z, we want to know proportionally what percentage of the distance from n to f is that. So we divide this value by f minus n, and we have effectively a percentage, which we want to then apply to the full new length that runs from -n to f, whose distance is equivalent to f plus n. The last step is to subtract n, because before we subtract n, we have a value which is in the range from 0 to f plus n, not -n to f. So if we subtract n, now it's in the range of -n to f. Now we have the formula for z of clip space, but the problem is it involves first subtracting from z, then doing a multiplication, and then another subtraction. But for a projection matrix, we're going to need to express this as a single multiplication and addition. We can't have that subtraction between the multiplication. Fortunately, if we go through a few steps, we can work out an equivalent formula, which is z times f plus n divided by f minus n minus 2nf over f minus n. And so now we have a formula we can plug into our projection matrix. So what the projection matrix is going to look like then is x is going to get simply multiplied by n over half the width of the view plane. The y values are going to get multiplied by n over half the height of the view plane. The z values are going to get multiplied by f plus n over f minus n, and then we subtract out 2nf over f minus n. And lastly, the w values is just the z value multiplied by 1, so the z value verbatim. And that's how we get from view space to clip space, by applying this projection matrix. Except again, actually I lied to you in the prior video. The camera in OpenGL is presumed to be facing down the negative z-axis, so all of our z values are in the negative range, not positive. And so going to clip space, first thing is we actually want to flip the sign of our z values and then apply the formula. So effectively that just means we need to flip the sign of f plus n. And then for our w values, because the x, y, z's of clip space are going to be divided by the w to get to NDC, normalized device coordinates, well, we don't want the w values to be negative because then all the signs would flip. So we're taking the z value, flipping its sign, and that is what the projection matrix calculates for w. So now, for the perspective call that was in our code sample, if we actually run the numbers, what we should get is a projection matrix that looks like this. For the x values, it's about 1.8. For the y values, it's about 2.4. For the z values, we multiply them by about -1 and then subtract 0.2. And for the w values, as always, we simply multiply the z by -1. So back in our code here, I'm going to add this line that will print out the value of the projection matrix, and we can verify if this is the case. So I'm going to build the code, run the program. And what do we see? Well, 1.8 checks out so far. 2.412, that's good. That's what we expected. And then -1, -1. Wait a minute, if this is the third row, something's off. And then on our fourth row, it's not -1, it's -0.2. So strangely, it looks like these two values are swapped, to the -0.2 and the -1. Well, what's simply going on here is that for whatever reason, when it prints out these 4x4 matrices, what we're seeing are the columns, not the rows. So this first group of 4 numbers is the first column, the second group of 4 numbers is the second column, the third group of 4 numbers is the third column, and then this is lastly the fourth column. So it is correct, it is what we expected. It's just printed out in column major order rather than row major order like we expected.